On the 7th of December 1941, Japanese forces struck Pearl Harbor, and within hours, the entire strategic calculus of modern warfare shifted on a single axis that military planners had consistently overlooked. Winston Churchill addressed Parliament on the 8th of December, outlining Britain's entry into what was now a truly global conflict. The Royal Air Force possessed 2,034 operational aircraft. The Luftwaffe fielded approximately 3,400. Britain's tank production stood at 4,841 units for the year. Germany had manufactured 5,200, but the numerical disadvantage was only the beginning. Every British aircraft, every military vehicle, every piece of mobile equipment relied upon a single critical component that Britain could no longer obtain: rubber tyres, rubber seals, rubber hoses, rubber insulation. The mathematics were brutal. Britain's military expansion required 600,000 tons of rubber annually. Current stockpiles would last 4 months. Domestic production capacity stood at precisely 0 tons per year. The crisis extended far beyond simple scarcity. 97% of the world's natural rubber came from plantations in Malaya, the Dutch East Indies, and French Indochina. By February 1942, Japanese forces controlled every single source. Britain's rubber supply didn't diminish gradually through attrition or submarine warfare. It ceased entirely within 12 weeks. The Dunlop Rubber Company, which had manufactured tyres in Britain since 1889, imported every kilogram of raw material from Southeast Asian plantations owned by British colonial interests. Avon Rubber, India Tyres, Firestone's British operations, all dependent on the same supply chain that no longer existed. Military planners calculated requirements with increasing desperation: 550,000 tyres for trucks, 180,000 for aircraft, 95,000 for tanks and armoured vehicles, millions of smaller components. Production capacity without raw materials: 0. The situation appeared unsolvable because rubber manufacturing wasn't simply a matter of industrial capacity. Natural rubber possessed unique properties that had defied synthetic replication for decades. Temperature cycling from -40 degrees Fahrenheit in high-altitude bombers to 180 degrees Fahrenheit in tropical combat zones, resistance to petroleum products, hydraulic fluids, and aviation fuel, flexibility under explosive decompression, durability through thousands of landing cycles. German chemists at IG Farben had developed synthetic rubber called Buna S in 1929, but it was inferior to natural rubber in nearly every performance metric and required enormous quantities of petroleum feedstock that Germany itself lacked. American companies had experimented with neoprene, but pre-war production totaled just 8,000 tons annually, 1% of British military requirements. The expertise, the patents, the manufacturing knowledge concentrated in a handful of German and American corporations, and Britain had access to neither. William Brocklehurst, born in 1869 in Macclesfield, Cheshire, had spent his youth working in his father's silk mill, surrounded by the chemistry of dyes and textile treatments. He showed no particular academic distinction, leaving school at 14 to enter the family business full-time. By 1891, he was managing chemical supplies for the mill, purchasing compounds from Germany's burgeoning chemical industry. A chance conversation with a German supplier introduced him to coal tar derivatives, waste products from gas manufacturing that German chemists were transforming into synthetic dyes, medicines, and industrial solvents. Brocklehurst became fascinated by the idea that complex organic molecules could be synthesized from simple industrial waste. In 1897, a fire destroyed the Brocklehurst silk mill. The insurance settlement was insufficient to rebuild, and at 28, Brocklehurst found himself without profession or prospects. If he couldn't manufacture silk, perhaps he could explore the chemistry that had intrigued him. He enrolled at Owens College in Manchester, studying organic chemistry under Professor Harold B. Dixon. His thesis examined the polymerization of isoprene, a hydrocarbon found in small quantities in coal tar, and also the primary constituent of natural rubber. Natural rubber was polymerized isoprene, chains of molecules linked together in specific configurations. In theory, if isoprene could be synthesized and controlled, synthetic rubber could be manufactured. Every chemist knew this. The problem was that controlled polymerization had never been achieved outside of natural biological processes. Brocklehurst's innovation came from an unexpected direction. Rather than attempting to synthesize pure isoprene and polymerize it, he experimented with co-polymerization, combining isoprene derivatives with other molecules to create hybrid materials. In 1902, he produced a substance from coal tar naphtha and butadiene that exhibited rubber-like properties. It wasn't rubber. It was brittle at low temperatures, degraded rapidly when exposed to oxygen, and possessed terrible tensile strength. But it could be vulcanized, it could be molded, and it could be produced from materials available in Britain. He published his results in the Journal of the Chemical Society in 1903, noting that whilst the material was unsuitable for commercial use, the principle of synthetic elastomer production had been demonstrated. The British chemical industry showed polite but limited interest. Natural rubber from British colonial plantations cost £60 per tonne and performed magnificently. Brocklehurst's synthetic material cost £340 per tonne to produce and performed poorly. There was no commercial case for development. Brocklehurst returned to industrial chemistry, working for various dye manufacturers, but he continued experimenting with synthetic rubber compounds in private. By 1910, he had improved his formulation significantly, using styrene copolymerized with butadiene extracted from petroleum cracking processes. The material still couldn't match natural rubber's performance, but it was approaching viability for specialized industrial applications where exposure to petroleum products made natural rubber unsuitable. In 1914, when war severed Germany's supply of colonial rubber, Brocklehurst offered his synthetic formulations to the War Office. They tested samples, found them inadequate for military applications, and declined. Germany, facing identical shortages, pursued their own synthetic rubber program with greater urgency, developing methyl rubber that was used in limited quantities for U-boat components and specialty applications. After the war, with natural rubber supplies restored, both German and British synthetic rubber programs were largely abandoned. Brocklehurst died in 1921, having spent 2 decades developing technology nobody wanted. But his notebooks remained. In 1926, chemists at the Imperial Chemical Industries Research Facility in Billingham discovered Brocklehurst's papers in their archives. ICI had been formed through a merger of British chemical companies and was actively seeking new product lines. A young chemist named Wallace Carruthers, who would later move to DuPont and invent nylon, reviewed Brocklehurst's work and recognized that advances in catalytic chemistry since 1914 might make synthetic rubber viable. ICI assigned a team to develop the concept further. By 1935, they had created a butadiene styrene copolymer they called Buna-Brit, which matched approximately 70% of natural rubber's performance characteristics and could be produced for £180 per tonne. Still too expensive, still inferior, but vastly improved. ICI built a small pilot plant in 1937, producing 200 tons per year of Buna-Brit for specialty applications, chemical-resistant hoses, oil seals, conveyor belts in environments where natural rubber failed. The material found modest commercial success, and ICI expanded production to 800 tons annually by 1939. Several British tyre manufacturers experimented with blending 5 to 10% synthetic rubber into natural rubber compounds to extend supplies and improve certain performance characteristics. Pre-war, this was an interesting marginal technology. In February 1942, it became Britain's only option. When Japanese forces captured Singapore on the 15th of February 1942, Britain's last major rubber stockpile fell into enemy hands. The Ministry of Supply conducted an immediate assessment. Current stocks, 180,000 tons, sufficient for 7 months at minimum military consumption rates. Required production to maintain operations, 600,000 tons annually. Available natural rubber imports, 0. Synthetic production capacity, 800 tons per year. The mathematics were impossible. Even if every military tyre, every seal, every hose were manufactured from pure synthetic rubber, which couldn't be done because synthetic rubber lacked the necessary performance characteristics, ICI's existing facilities could supply less than 0.1% of requirements. Lord Beaverbrook, Minister of Supply, summoned ICE's chairman, Sir Harry McGowan, to an emergency meeting on the 24th of February. The conversation was direct. Could synthetic rubber production be scaled to meaningful quantities, and could the performance gap be closed? McGowan's technical director presented the constraints. Bunabrit production required butadiene derived from petroleum, styrene synthesized from benzene and ethylene, and complex catalytic polymerization in temperature-controlled reactors. Building new production capacity would require 2 to 3 years. Developing improved formulations to match natural rubber performance would require extensive research. They didn't have 2 years, they had months. McGowan proposed an alternative. ICI had been investigating rubber extraction from domestic sources as a contingency. Russian dandelions, Taraxacum coxsackies, produced latex with rubber content approaching 8%. Trials in Yorkshire had yielded 200 kilograms of rubber per hectare. Germany was already cultivating dandelions and domestic plants for rubber production, though yields were marginal. Additionally, ICI believed they could improve Bunabrit's formulation significantly if given resources and priority access to petroleum feedstocks. The proposal, a dual approach, rapid scaling of existing synthetic rubber production whilst simultaneously developing improved formulations, emergency cultivation of dandelions and other latex-producing plants to supplement supplies. Target: 100,000 tons of synthetic rubber within 12 months. The Cabinet approved unlimited funding on the 2nd of March 1942. ICI immediately began construction of new polymerization facilities at Billingham, Grangemouth, and Wilton. The scale was staggering. Billingham's expansion alone required 8,000 construction workers, 450,000 tons of steel, 2.2 million bricks, and 15 kilometers of high-pressure piping. Existing butadiene production capacity was 1,200 tons per month. Plans called for 12,000 tons per month by September. Styrene production needed to increase from 800 tons monthly to 9,000 tons. Every expansion depended on petroleum refining capacity that was simultaneously supporting increased aviation fuel production. Dr. Geoffrey Stafford, ICI's chief polymer chemist, led the formulation improvement program. Brocklehurst's original copolymer ratios were 60% butadiene, 40% styrene. Stafford's team experimented with varying ratios, different catalysts, alternative polymerization temperatures, and cross-linking agents. By May 1942, they had developed Bunabrit Mark II, 70% butadiene, 30% styrene, polymerized with a potassium persulfate catalyst at 50 degrees Celsius rather than the 80 degrees Celsius used previously. The lower temperature produced longer, more uniform polymer chains. Tensile strength improved by 34%. Low temperature flexibility improved by 28%. Resistance to oxidative degradation improved by 41%. The material still couldn't match natural rubber, but it was approaching suitability for critical military applications. Production scaling proceeded with brutal intensity. In March 1942, ICY's 3 facilities produced 1,847 tons of synthetic rubber. In April, 3,654 tons. In May, 7,221 tons. The growth came at extraordinary cost. Reactor operators worked 12-hour shifts in temperatures exceeding 95 degrees Fahrenheit. Butadiene was toxic. Exposure caused neurological symptoms. Styrene vapors caused respiratory problems. Safety equipment was inadequate. Margaret Thompson, age 23, a reactor operator at Billingham, later recalled, "We knew the vapors were making us ill. Headaches, dizziness, nausea. But we also knew that every ton we produced meant tyres for lorries carrying ammunition to North Africa, seals for aircraft flying over Germany." Dr. Stafford came to the floor one evening, watched us working, and said, "This rubber will keep pilots alive." That's what mattered. By June 1942, monthly production reached 11,400 tons. The facilities operated at 127% of designed capacity, running continuously with maintenance conducted in rotating 30-minute shutdowns. Worker injuries occurred at rates 4 times pre-war industrial averages. Material shortages plagued every stage. Benzene for styrene synthesis competed with explosives production. Ethylene competed with plastic manufacturing for radar components. Petroleum refining capacity couldn't expand fast enough. ICI began importing styrene from American producers, paying premium prices and risking U-boat interdiction during Atlantic crossings. The Ministry of Supply established a tyre development committee to test synthetic rubber compounds in military applications. Trials began in July 1942 with aircraft tyres, the most demanding application. Specifications required survival of 200 landing cycles at loaded weights up to 40,000 pounds, temperature ranges from -40 degrees Fahrenheit at altitude to 180 degrees Fahrenheit on tropical runways, resistance to aviation fuel and hydraulic fluid, and maximum degradation not exceeding 15% after 500 hours of operational use. Natural rubber tyres routinely exceeded these specifications. Pre-war synthetic rubber failed catastrophically within 30 landing cycles. Dunlop, Avon, and India tyres each produced test batches using Buna Brit Mark II. Results from initial trials in August 1942 showed dramatic improvement over pre-war synthetic formulations, but still fell short of natural rubber. Average failure point: 87 landing cycles. Temperature cycling caused 23% degradation after 500 hours. Petroleum exposure caused surface cracking. The results weren't close to natural rubber, but they exceeded the ministry's minimum acceptable performance threshold of 75 landing cycles and 30% degradation. On the 15th of August, the ministry authorized production of 50,000 aircraft tyres using 75% synthetic rubber, 25% reclaimed natural rubber from salvaged tyres. Stafford's team continued formulation refinement. In September 1942, Buna Brit Mark III introduced carbon black reinforcement and antioxidant additives that further improved durability. Testing showed 134 landing cycles before failure, 18% degradation after 500 hours. By October, Mark IV achieved 156 landing cycles. The gap was closing. Production simultaneously continued scaling. September 1942, 18,900 tons. October, 24,300 tons. November, 31,200 tons. December, 38,700 tons. ICI's facilities now produced more synthetic rubber in 1 month than total annual production in 1939. The agricultural program provided marginal but meaningful supplementation. By autumn 1942, Yorkshire, Kent, and Devon farmers had planted 12,000 hectares of Russian dandelions under emergency cultivation orders. Harvest yielded 1,840 tons of rubber, less than 2 days' worth of synthetic production, but every ton mattered. Processing facilities at Hull and Dover extracted latex, coagulated it, and shipped crude rubber to tyre manufacturers. The program expanded in 1943 to 35,000 hectares, yielding approximately 6,000 tons annually. German dandelion cultivation was larger but faced identical constraints: enormous effort for marginal output. Combat validation began in North Africa in November 1942. The RAF's 112 Squadron, operating Curtiss Kittyhawk fighters from Landing Ground 91 near El Alamein, received aircraft equipped with Buna Brit Mark III tyres. Flight Lieutenant James Morrison flew 17 sorties between the 8th and 24th of November, conducting ground attack missions against retreating German forces. His aircraft's tyres endured 23 landing cycles on improvised desert airstrips, rough-graded sand and gravel that abraded natural rubber severely. Morrison's maintenance log noted, "Synthetic tyres showing surface wear but no structural degradation, performance equivalent to natural rubber under these conditions." Similar reports arrived from bomber squadrons. Halifax bombers of 76 Squadron, operating from Linton-on-Ouse, used synthetic rubber seals and hoses throughout their hydraulic systems. Between December 1942 and March 1943, the squadron flew 287 combat sorties over Germany. Maintenance records showed hydraulic seal replacement rates of 3.2% per 100 flight hours, compared to 2.8% for natural rubber seals. The difference was statistically marginal. Squadron leader Peter Ward reported, "No operational losses attributable to synthetic rubber component failure. No mission aborts from hydraulic problems related to synthetic seals. Material performs adequately under combat conditions." Tank units provided the most demanding test. Churchill tanks weighed 40 tons, operated in North African temperatures exceeding 120 degrees Fahrenheit, and subjected tyres and track support rollers to continuous punishment across rocky terrain. The 7th Armoured Division received Churchill tanks with hybrid rubber components in January 1943. Over the subsequent 6 months during the Tunisia campaign, maintenance logs showed track support roller failure rates of 8.1% per 1,000 kilometers with synthetic rubber components, compared to 6.4% with natural rubber. Higher failure rates, but acceptable within operational parameters. 0 combat losses resulted from rubber component failure. German intelligence obtained samples of British synthetic rubber through captured equipment. A translated document from the Reichsministerium für Bewaffnung und Munition, dated April 14, 1943, noted, "Analysis of British synthetic rubber compounds indicates butadiene-styrene copolymer composition, similar to our Buna formulations, but with superior low-temperature performance and oxidation resistance. Manufacturing quality is high. British synthetic rubber production capacity appears to exceed our current estimates. Their ability to field fully operational military forces despite loss of natural rubber supplies suggests synthetic production of at least 250,000 tons annually." The estimate was conservative. By mid-1943, British synthetic rubber production exceeded 420,000 tons annually. Germany's own synthetic rubber program faced cascading problems. Buna production required petroleum-derived feedstocks, but German petroleum supplies were critically limited and prioritized for aviation fuel and diesel production. Buna plants at Schkopau and Hüls operated below 60% capacity due to feedstock shortages. Allied bombing raids on petroleum refineries and synthetic fuel plants in the Ruhr further constrained production. By late 1943, German Buna production was declining whilst British production continued expanding. The window for Germany to develop comparable synthetic rubber capacity had closed before the war began. The strategic bombing campaign against German industry included persistent attacks on Buna production facilities. On the 22nd of May 1943, RAF Bomber Command dispatched 153 aircraft to attack the Hüls synthetic rubber plant. The raid destroyed 35% of production capacity and killed 186 workers. Follow-up attacks in June and August caused additional damage. American daylight raids in 1944 struck Stockpiles repeatedly. These attacks disrupted German synthetic rubber production, but the impact on Germany's overall war capability was limited by stockpiles and continued imports from occupied territories. The irony was stark. Whilst British bomber crews died attempting to destroy German synthetic rubber plants, Britain was producing superior synthetic rubber in quantities that exceeded its own requirements and allowed exports to Allied nations. The human cost of scaling synthetic rubber production was substantial, but rarely quantified. Between March 1942 and May 1945, ICY's synthetic rubber facilities recorded 847 industrial accidents requiring hospitalization, 127 cases of chronic chemical exposure requiring permanent reassignment, and 23 fatalities. The deaths resulted from explosions, toxic gas exposure, and accidents involving high-pressure equipment. Workers understood the risks. Production never slowed. By 1944, ICI employed 14,200 workers in synthetic rubber production, 67% of whom were women. They produced 520,000 tons that year, nearly matching Britain's pre-war natural rubber consumption from colonial sources that no longer existed. Post-war, Britain's synthetic rubber industry expanded rather than contracted. ICI's production capacity reached 680,000 tons by 1950. Natural rubber supplies from recovering Southeast Asian plantations became available again, but synthetic rubber had proven superior for many applications. Aircraft tyres, military vehicle components, chemical-resistant industrial products, all used predominantly synthetic compounds. The technology descended from William Brocklehurst's 1902 experiments, refined through decades of marginal commercial interest, and scaled to industrial significance only when desperation demanded it. Modern synthetic rubber production exceeds 16 million tons annually worldwide. Britain produces 340,000 tons, exported globally for automotive, aerospace, and industrial applications. Every modern tyre uses synthetic rubber compounds. The formulations have advanced far beyond wartime Buna Brit, incorporating styrene butadiene rubber, polybutadiene, ethylene propylene diene monomers, nitrile rubber, but the fundamental chemistry remains. Copolymerization of petroleum-derived monomers using controlled catalytic processes. The technology that Britain developed from coal tar and petroleum in 1942 now dominates an industry that was entirely dependent on plantation agriculture in 1941. The historical reversal is complete. In 1941, 97% of rubber came from British and Dutch colonial plantations in Southeast Asia. Japan controlled 0%. By 1943, Japan controlled the plantations, but lacked the industrial chemistry to produce synthetic alternatives. Britain, which had controlled the natural rubber supply, lost it entirely, but developed synthetic production capacity that exceeded pre-war natural rubber consumption. Germany, which had pioneered synthetic rubber development in the 1920s, couldn't produce sufficient quantities due to petroleum shortages and Allied bombing. By 1945, Britain was exporting synthetic rubber to the United States, which had its own massive synthetic rubber program, but valued British formulations for specific military applications. The nation that entered the war with zero domestic rubber production capacity ended it as a major rubber exporter. German chemical engineering, which had dominated the field for decades, came in second place,